Alrighty, good morning or good afternoon, ladies and gentlemen. Happy Friday if you're there with me. Today we're going to actually depart because we finished up our polynomials unit. We're going to talk about deduction and induction. So this is part of our logic and reasoning. Notice how I've been giving a lot of logic puzzles. So low-key, you've actually been doing deduction and induction to solve these puzzles. I'm going to actually formally define what they are and also give you some strategies to look for when you're solving these kind of logic puzzles or number puzzles. So the two things we're going to look at are two methods of reasoning called deduction and induction. So broadly, I have two definitions here on our screen. Deduction moves from idea to observation. You may have heard the whole Sherlock Holmes. Oops. So Sherlock Holmes always talks about deduction. He's like, deduction, dear Watson, while induction moves from observation to idea. So the idea is that you see something and then you make a theory. Whereas Sherlock Holmes has a theory and then he looks for things to prove that theory right. So these sort of work opposite to one another, and in certain cases, deduction works best, and in other cases, induction works best. So deduction is idea first, followed by observations, and then a conclusion. And induction is observation first, followed by an idea that would explain what's been seen. So oftentimes, induction is looking for patterns, and deduction uses, I'll say, truths to lead to a conclusion. And whereas induction looks for patterns to make theories, I'm going to show you a couple different ways. So here's a good example of deduction. We start with an idea or a premise, and the thing about this is that it has to be true. For deduction, all of what we say has to be true for a conclusion to be true. So it starts out with, all men are mortal. This is a true statement. People pass away. Next up, we follow it with an observation. Jason is a man. Sure. We'll assume that this is true. So the conclusion that you can make is that Jason is mortal. The thing is that both of these need to be true. If for some reason there was someone who was immortal, then Jason could be that immortal, and then it's not a true statement. I'll talk about this using a little bit of a better example, but first we're going to look at the idea of induction. So induction starts with an observation. So I break out when I eat peanuts. The analysis, you're looking for a pattern. So if every time you eat peanuts, you have this sort of breakout reaction, you can make a connection that this is a symptom of being allergic. So this is sort of a pattern that we're looking for, or a connection. And then the theory is that I'm allergic to peanuts. Every time I eat peanuts, I feel crappy, I break out in hives, and that's what people who are allergic to peanuts get, so I'm probably allergic to peanuts. The thing about this is that not always true. Maybe there's a different explanation for why the person breaks out when they eat peanuts. Maybe they only eat peanuts when they're being attacked by bees and they're actually allergic to bees. So the difference is deduction is really good at getting true statements provided we start with true statements. Induction is a form of reasoning that can lead us to the best possible theory that we can then test and retest. So oftentimes, another way we can think about it is deduction. We start with a theory or a premise. We make a hypothesis. We observe it, and then we confirm it, and then we can go back here and keep going around. For induction, I make an observation. So notice how the observation was near the bottom. I make a pattern, I make some sort of hypothesis, and then I have a theory. So it comes back around and I can test that theory. So notice how in both cases we have a hypothesis, we have a theory, but in either one that we're working and coming about them a slightly different way. In science, oftentimes we use both induction and deduction to solve for things. So when you're doing a science experiment, you can use some things deductively, like all things on Earth fall towards the ground, and you can use that to make a conclusion of where the ground is. If you drop something and it falls sideways, you're probably lying on your side. In other cases, you'd want to use induction to explain what you're seeing. So let me give a couple of word examples of how these feel different. So a deductive argument might be something like, all raccoons are omnivores, the animal I see is a raccoon, therefore this animal is an omnivore. Notice how in this case I need this to be true and this to be true. Oftentimes if you see a raccoon, sure, that's not a hard thing to make a conclusion of. But we also have to conclude that all raccoons are omnivores. Now, I can test, but it's hard to do. But in this case, if I assume it's true, then this would also hold. An induction pattern is 4 of your classmates order the same sandwich, therefore the sandwich is probably good. Does it mean the sandwich is good? No. So the difference is the sandwich might be good. In this case, they say probably. So at this point, I would have to test it. Maybe there is another reason why your classmates are ordering the same sandwich. Maybe it's the cheapest. So in that sense, it's not the best one, or it's not good, it's just cheaper. But this allows us to make a theory based on what we see. So the key difference between a deduction argument and an induction argument is deduction, I'm going to start with a truth and look for an observation and then make a conclusion. In induction, I always start with something that I see. And the problem with either one of these, they're both excellent ways of making arguments and reasoning through logic problems. The problem arises when we use something that should use induction for a deduction style problem. So let me show you where this comes into problems. So most Labrador retrievers are friendly. Kimber is a Labrador retriever, therefore Kimber is friendly. Do you see the issue? For those of you who have dogs, or maybe don't have dogs and don't like dogs, not all dogs are friendly. The problem here is that we have assumed this to be 100% true. And even in this part, it says most. So I cannot assume, because it doesn't say all Labrador retrievers are friendly, because how could I prove that? So deduction makes arguments and then spits out a truth, but both of them have to be true. So Kimber is a Labrador retriever, probably true, but most Labrador retrievers are friendly. You can see that there's a chance that it'll be true, but there's also a chance that it'll be false. So on one hand, I have a false, and then on the one side, I have a true. So in some cases, I might get that Kimber is a friendly golden Labrador retriever, but in other cases, Kimber won't be friendly. Now, another example of this is Harold is a grandfather, Harold is bald, therefore all grandfathers are bald. This is again using an induction problem. Deductively. So sure, Harold is a grandfather, Harold is bald. Both of these are observations. and they are true. We'll assume them to be true because we're being told them. But what I can't do here is put those towards a general case. Another way I can think about these is that deduction starts general and we move to specific. So all men are mortal, Jason is a man, therefore Jason is mortal. We've moved from a general truth, or another thing that I could use deductively is all objects fall towards the earth. I can use that as a truth to then say something specific that if I drop my eraser, it's going to fall towards the earth. Induction starts with specific. I'm seeing something in front of me, and I move to a more general approach. So, for example, I notice that 4 of my classmates order the same sandwich, so generally I can make a generalization that the sandwich is probably good. Here, Harold is a grandfather, Harold is bald. I'm seeing something very specific, and I'm trying to apply it to something general. So, all grandfathers are bald. This is very general, so I can't use deduction. Now, let's look at some other things that we can do. So, things to look for in logic puzzles. So, one of the things I'll talk about is something called mutually exclusive cases. So this is a situation where if we have one thing to be true, all other options are false. So for example of a mutually exclusive case, if it's Tuesday, so if the day is Tuesday, then today is not Monday, Wednesday, Friday, oh, I missed Thursday, and then Saturday and Sunday. So one of the things to look for in logic problems is look at the information that's given to you, and it actually tells you 2 full pieces of information. In a lot of these cases, if it's something, then it means that it also is not something else, and we can rule that out as an option. And this is one of the best things to look for to start. Look for what the information that it gives you, and then look for hidden information that would mean that it's not something else. So, mutually exclusive cases, that's going to be one thing to look for in logic puzzles. So what the question assumes to be true is another good thing to look for. So an example of this is, if you remember that zombie bridge question, each person crosses in a specific time. Now this is debatable in real life, but for logic problems, we try to constrict ourselves to something that we can assume to be true. So if it gives you a specific time, use that time or that number or that information to help you out. Don't make any assumptions outside of it. So in our 3 hat problem, we had 1 blue hat, 2 blue hats, or 3 blue hats. So this question actually gives us more information. So that means our cases are that we have 1 blue, 2 white, 2 blue, 1 white, or 3 blue, 0 white. Which brings me to the last point, is look for cases. Or another way I can think about this is deal with the problem in small chunks and connect them together. So for example, that 3 hat problem is an example of both an induction and a deduction problem. You are using the information that's given to you to make certain deductions. Like, for example, pretty much all of you got, if there was 1 blue hat, that person would see 2 white hat people and they could immediately know, because of these rules, that their hat must be blue. Now this is part induction, part deduction. Induction by the fact that they are making a conclusion that may or may not be wrong, but based on the information that they've given them is the best answer. But they are also using deductive rules and deductive reasoning to rule out what is not the case. This is where it gets a little bit trickier, is that in this problem that I gave last week, you can use the results of that case to influence the results of this case by looking at what the other people see. So you're using induction to observe the reactions of the other 2 people, because you're going to see something and they're going to see something, or they're going to see the 2 different colored hats, or they're going to see 2 of the same colored hats, and each one is going to react accordingly, knowing the information about the case with 1 blue hat and 2 white. The last thing I want to go over is there is a type of puzzle. It was famously called an Einstein Puzzle because it was proposed that Einstein came up with it and that it's an exceptionally hard logic puzzle. It's also called a zebra puzzle because oftentimes these questions are asking who owns the zebra or who owns the fish. So this is an example of an easier version, so I can go through it a little bit quicker. But an easier version of the one that's on your assignment. So basically our goal is to fill out this entire thing and figure out the players, the lanes, and the scores. And notice how it says players and scores. So if Alberta had a point of 300, I'd put her here. I've got lanes and lanes, so then I can match up scores to lanes, and I can match up lanes to players. So this is one way that you can set it up because we have 3 different things in this case to deal with. But I'm going to look at the clues to figure out a couple things, and you will see how I apply these mutually exclusive cases and assumptions and connections to solve this puzzle. So first clue, Zachary was in lane 2. So it right away tells me Zachary was in lane 2, so I find lane 2 and Zachary. Now that implies more information than that. With these problems, if Zachary is in lane 2, then that means he's also not in lane 3, lane 4, or lane 7. And another thing about these is that each case happens exactly 1 time. So for example, if Zachary is in lane 2, then that means that Nina Hope, and Alberta are also not in lane 2. Now, I don't know anything else from that information, but I have gone from just knowing one piece of information to actually knowing 7 pieces of information. I know where Zachary is not, and I also know that one place where Nina, Hope, and Alberta are not. So I'm going to look at clue number 2. Alberta was in lane 3. So sorry about that. Alberta was in lane 3, so that means she is here, which means that she's not in lane 4 or lane 7, and Hope and Nina are not in lane 3. So Hope and Nina are in lane 4 and lane 7. I don't know which one, but there's that ruled out of the way. The person who scored 380 points is either Nina or the person in lane 2. So I know that Zachary is in lane 2, so it's either Nina or Zachary that are here. There's actually another piece of information, and it comes from this or. How I figured that out was Zachary is in lane 2, so that's how I got that piece of information, but I can also maybe use it for another piece. Before I do that, I'm going to look at my other clues. Nina scored 80 points more than the contestant in lane 2. Okay, well, that helps me out right away. So Nina scored 80 more points, so I see the points are 300, 380, 460, or 540. So now, it doesn't seem like I've gotten a lot of information, but what that actually means is that Nina can't be here. Because if she's scored more points, then I cannot put her in that lane. Or with that number of points, because it's the lowest number of points. And I also know that Zachary from clue 5 scored more points than the contestant in lane 7. So if Zachary scored more points, he also cannot be here, which means at minimum he has to be at 380 points. Now, this is where I can use inductive logic. Zachary has to score more points than the contestant in lane 7, and Nina has to score more points than the contestant in lane 2, which means that Nina can't score 380 points because Zachary can't score 300 points. So now, between those two, I know that Zachary is the one that scored 380 points, which means that I can get rid of these, I can get rid of these, and it also means that if Nina scored 80 more points, that Nina is going to be here. I also know that the lane 7 person will have scored 300 points. So I can cross those out. I can also do a bit of housekeeping and cross those out. Now it seems like I need more information. So let's see if I can look back at my other clues. So I have Alberta, I have Hope. Oh, okay. So Zachary scored more points than the contestant on lane 7, but Alberta's in lane 3, so she can't score this amount. So that means Hope has to be the one here, and Alberta has to be the one here. So I can cross this out. Hope is in lane 7, or the person who scores 300 points is in lane 7, so that means Hope is here. I can cross this out and this one out, which means that Nina must be in lane 4. And once I get here, I actually have enough to finish the whole thing. So lane 2 is Zachary, 380 points, so I can put my dot here. That gets rid of these. And then Nina scored 460 points and she's in lane 4. So that dot's going to go here and that dot's going to go here. And then I can cross those out. So the key bit, these ones give direct information or info. These ones I have to use induction, or deduction to get more information. I'm making connections with what I see from the other clues that I'm given to make the best logical choice. And then if I zoom out here, I can check my work and I can see that I've managed to solve this puzzle. So for these ones, notice what I did with some of these was I used the info to rule out impossible options. And this is a form of deduction. So for example, if Nina scored 80 more points than the contestant in lane 2, which I knew at this point was to Zachary, that Nina would have had to have been 80 points above wherever I put Zachary. So those two pieces of information were linked, and then I also knew that Nina couldn't be the lowest scoring person. Then I used the fact that Zachary scored more points to mean that Zachary couldn't be the lowest point. And then additionally, there was that third piece of information that said that Nina or Zachary had to have been there. So if this doesn't work for Zachary, this one can't work for Nina. And then I've ruled out all possible options. So Zachary has to be here, Nina has to be here, and I can use the other information to keep going. So that's all I have for you today. I have posted the assignment. Please look at this video. Keep looking back at it. I have this in our content library if you want to look at how I went through it and the notes, and use this to try to solve the problems. For the other riddles, they're a little bit more using universal truths. A lot of them are deduction problems, but these ones deal a lot more with numbers than the previous ones. So use what we've learned about logic and reasoning to clearly explain what is happening. That's all I have for you today. Take care, stay safe, have a good one, have a great weekend.